Welcome to the lecture for Chapter 12 on earthquakes. This week we're going to be looking into the causes and characteristics of earthquakes so that we can understand how seismic waves work. We want to be able to appreciate the range of damage associated with earthquakes and how geophysics is used to explore the Earth's interior. So before we get started, I want you to stop for just a minute and think about what you already know about earthquakes. So you've already read the chapter, you've seen movies, you've seen the news, perhaps you've been in an earthquake yourself. What do you already know about earthquakes? Do they come in different sizes? Are they all devastating? Do they happen absolutely everywhere? Recall back to our plate tectonics lecture. These are the kind of things you want to note just to sort of get your brain started on what you already know about earthquakes. This first example here is the Indonesian earthquake and resulting tsunami. So in looking at this image, the length of the rupture zone is shown by the red line. The black labeled lines represent travel times in hours of the tsunami as it radiated out from the earthquake zone. So if you look, the first line out is labeled 1. That's 1 hour out. And then all the way out to the coast of Africa, we see it gets all the way to 11 hours out. So within 11 hours, it has traveled from the rupture zone all the way to the coast of Africa. And notice that the spacing between those travel timelines is pretty even. So the tsunami, as it's moving, is maintaining a steady speed. The curving of the lines is important as well. Just like if you drop a pebble in a pond and the waves radiate out, the curving of the lines as the tsunami wraps around land masses is important. The earthquake itself ruptured along a 1,200 kilometer, about a 760 mile length, as a section of the Eurasian plate was uplifted. The ocean floor above the rupture was lifted several meters, causing the tsunami. So in an instant, the ocean floor moved up several meters. This is a huge deal. Most of the time the plates are moving at about the rate that your fingernails grow. So to have something move several meters in an instant is incredible. So as the seafloor basically jumped up several meters, it pushed all of the water above it up, and that's what caused the tsunami. The tsunami traveled 800 kilometers per hour, which is about 500 miles per hour, on average away from the rupture. It arrived within minutes in Indonesia, and 7 hours later it reached the east coast of Africa. The loss of life was tremendous for this disaster, just unbelievable, and it depended primarily on population concentration along shorelines and the distance from the rupture. So that gets at wave energy dissipation. So basically the energy of the wave is dissipating, or the wave itself is getting weaker with time as it gets further away. So all of this information is getting at why it's important to understand earthquakes. This was a huge event. In Indonesia alone, you can see on this image the loss of life was 167,736 people. You know, that is devastating. That is a huge number of people, and thousands more died outside of that direct area. So why do we want to understand earthquakes? So that tragic events like the 2004 Indonesia earthquake do not occur. Okay, this earthquake was located at a subduction zone between the Indian and Australian plate because it was underwater, it caused a giant tsunami. We could not have stopped the earthquake. We could not have stopped the tsunami. But if proper warning systems had been in place, much of the loss of life could have been prevented. So we've got a before and after shot here. On the left we're looking at before the tsunami, on the right we're looking after the tsunami. So examine these two photos and note the differences before and after the 2004 tsunami. Just take a minute. What do you see that's different? Look along the coastline. Look inland. What's different? So what I see when I look at these is in the before view, the vegetation is green. The browns and reds in the before image are building roofs. In the after view, the brown, tan, and light colors are just bare earth. The vegetation has been stripped or buried by sediment. The white squares are building foundations. So whatever buildings were there have been completely stripped off. So that's what this photo is showing us here. These white squares in the foreground are foundations of buildings. The tsunami was driven across land from left to right, from the ocean inland. Buildings and vegetation were destroyed in low areas. The higher ridge to the north was relatively unaffected, and the fringing reef with breaking waves is shown in both images. But you can see how the sediment along the shoreline is swirling out into the ocean. We've lost a lot of beach area there. So we know that earthquakes are destructive. We know that they can cause tsunamis. But what is an earthquake? An earthquake is the shaking of the ground by the passage of seismic waves resulting from a release of stress. An earthquake is the shaking of the ground by the passage of seismic waves resulting from a release of stress. Most earthquakes occur along faults when stress builds up, eventually causing the fault to slip. So when it does slip, we get these seismic waves radiating outward from the hypocenter. And we've got two dots on our image here that's showing us a number 1 with a dot and a number 2 with a dot. These are representing seismic stations, so locations where seismic waves are being recorded or where earthquakes are being studied and measured. So seismic stations, the wave is going to arrive at the closer seismic station first. So you can think of this again like a pebble dropping in water. It's just going to radiate outward from that point. So the closer you are to where the pebble dropped, or the closer you are to the epicenter, the point on the surface where those waves start to radiate out, that's where you're going to feel the seismic waves first. Alright, so in describing earthquakes, the rupture begins along a small section or point on the fault, which is the hypocenter. So that's that little star that's below ground. That is called the hypocenter. First, the seismic waves arrive at the closest point on the surface. That is called the epicenter. So directly above the hypocenter, we get the epicenter. So the epicenter is the point on the surface that is closest to the hypocenter. Causes of earthquakes. So we've got 3 different types of faults here, and the small black arrows show relative movement along the fault. The blue arrows show stresses applied to the block that cause the block to move. In the left, the stress is tension, right? Just like when we talked about divergent boundaries, but this is on a smaller scale. So when we have tension applied at a fault, we get what's called a normal fault. When we have compression that center image applied, it's a reverse or a thrust fault. When we squeeze them together, that's tension. And when they move side by side, when we have that shear stress, that's called a strike-slip fault. So just to describe what's going on at these different types of faults, on the left, the normal faults, the crust is getting thinner. So we look at the center there. There's less rock in the center than there is on the edges. For reverse and thrust faults, the crust is getting thicker. Right there at the center, we're stacking the rocks. And then for the strike-slip fault, we have horizontal displacement only. Nothing's moving up or down. It's just moving side by side. Okay, so we can also generate seismic waves at volcanoes. So on your next page of notes, we're continuing with what causes earthquakes. The image on the left side of your notes is just another picture of that normal fault. So all you need to write there is movement along faults. The next image is this volcano, and that's what we're going to talk about right here. So volcanic eruption, movement along faults, slope failure or landslides, and movement of magma can cause earthquakes around volcanoes. So just to elaborate that a bit, explosive eruptions or volcano erupting generates seismic waves, as does the movement of liquid magma. So the movement of the magma below the surface as well as the explosive eruption is sending out these waves of energy, the seismic waves. Movement along faults. Normal faulting occurs as blocks slide into empty magma chambers. Slope failure. Unstable rocks on steep sides of a volcano may fail during shaking. So if you have an earthquake, that can trigger a landslide and that can trigger an eruption. That's what happened at Mount St. Helens. So elaborating on that even further, an example is Hawaii. So Hawaii is subjected to massive underwater landslides that are capable of generating large tsunamis. So that takes us to the next point in your notes, landslides. So on land, it does not send out as large an earthquake, but underwater earthquakes are so much bigger because you've got the water there lubricating the movement of the rocks. So landslides on land or underwater can cause earthquakes. The next one is meteoroid impacts. Meteoroid impacts are likely to generate the largest seismic waves, some perhaps causing mass extinction. So when you think about the extinction of the dinosaurs, that's usually associated with a very large meteorite impact. Because when it hits the Earth, it's with such force, and if it's a large enough object, it pulverizes everything it's coming into contact with and sends it out as ash, really. It's incredible. The next one is explosions generated by humans. So these two seismic readings here are showing us nuclear tests that create distinct pulse-like seismic signals. So the red line on the top is showing the Indian nuclear test. So you get a big initial pulse and then a few small pulses after, sort of petering out. Whereas with the earthquake, you start out small, you get larger, it fluctuates a bit, and then dies off. So they have a very different seismic signature, but this is a good way that military information and scientific information overlap. So if we have more seismic stations around the globe, we are safer because we can give people more notice that a tsunami or something is heading their way, but it also has a security aspect where we can tell if nations that we don't trust or are giving us misinformation, we can tell if they're testing weapons and things like that. Taking a look at what's going on here in a strike-slip earthquake, first we're going to look at what happens before. So before, the stress increases until it can overcome the frictional strength of the rocks. The stress increases until it can overcome the frictional strength of the rocks. During this time, the rocks are strained, resulting in them being squeezed, pulled, and sheared. In the next image, during, we have slip of the ground. So now the rocks are moving. Slip of the ground, releasing the stored up stress, resulting in an earthquake. So you can see the part on the right or furthest from us is moving to the left, and the block that's closer to us is moving to the right. Afterward, aftershocks occur as the ground settles under the new conditions and stress begins to build again. So we're starting this whole process over again. So to summarize, we have strain along the fault building up. It releases through fault movement. In this case, the fault underlies the river. And that's pretty common because you'll end up getting a depression along that fault or a fault scarp. So one side will be higher than the other, and it's easy to erode a river down along the fault. The river location is controlled by easily eroded rocks there in the fault zone, so that's why we get it there. There may not be an alternative location for this section of road, so it's always rebuilt, even after being destroyed. So you can see that the old bridge that was over the river in the first image had to be rerouted and rebuilt. And that's really common. So when you come across an abandoned stretch of road or bridge, it's kind of neat to look around and see if something like this happened or if they were just upgrading. But it's pretty neat and very common. Okay, looking inside to see what's going on with the faults. How do earthquake ruptures grow? A rupture starts as a small patch below the Earth's surface. That's what this little dark oval is representing. A small patch below the Earth's surface and begins to expand along the fault line. As the rupture migrates outward, it may eventually reach the Earth's surface. That causes a break at the surface. That's what we call the fault scarp. Over time, the fault scarp lengthens out. The rupture continues to grow along that fault plane. The rupture stops when the stress can no longer overcome the friction along the fault plane. Okay, so the force that's generating this fault only continues to move, only continues to rupture the rock when the rock is basically soft enough that it's able to break and move along it. When the force decreases, then you won't get any movement along it. So taking a look at some photos, we've got this photo on the left. The scarp cuts weathered granite. This is in the Mojave Desert in California, just after the Landers 1992 earthquake. This one we're looking at Bora Peak, Idaho, after the 1983 earthquake, and this is looking at a fault scarp in alluvium. So alluvium is the debris that's coming off of surrounding mountains down into the valley. So, some things for you to think about. How long can a fault scarp survive as a sharp surface expression in unconsolidated material versus hard rock? Okay, this is just a little something for you to think about. Is a fault scarp going to survive as a sharp surface expression in unconsolidated material, so meaning a pile of loosely consolidated or loosely packed together gravel or sand versus something that's very hard like granite? Okay, another question for you to consider is what stops an earthquake rupture from propagating forever? Okay, why doesn't it just spread around the whole world? What happens? Just something for you to think about. I've hinted at it, but we'll come back to that concept again. Where earthquakes occur. So this is a very familiar image. We saw this when we were talking about plate tectonics. And now we want to describe how plate tectonics plays a role in the creation of earthquakes. So in this image we have yellow dots that represent shallow earthquakes, green dots that represent intermediate depth, and red that represent deep earthquakes. Earthquakes are not everywhere, but they occur in belts. There is a broad kind of chaotic arrangement of earthquakes that occur in Asia as well. So again, earthquakes occur in narrow belts coinciding with plate boundaries. Mid-ocean ridges have shallow earthquakes. Deep and intermediate earthquakes occur in subduction zones. And the collision of India and Asia is still occurring, resulting in intermediate to shallow earthquakes across that broad region where the Tibetan Plateau is in between India and the rest of Asia, so where the Himalayas are. Okay, so as far as describing how plate tectonics plays a role in the creation of earthquakes, okay, we already said they occur in belts. You get shallow ones at the mid-ocean ridges. You get deep and intermediate earthquakes at subduction zones. And you get intermediate to shallow earthquakes in continent-continent collision zones, like that in the Himalayan mountains. Okay, so pointing out where some of those are. We've got subduction zones, and just to talk about that a little bit more, remember a subduction zone is a result of a convergent boundary. So we have compressional stress, it's being squeezed together, and that creates reverse and thrust faulting throughout the region. We get large earthquakes that occur along the entire contact between the subducting plate and the overriding plate. The earthquakes go from shallow at the trench, right near the surface, to deeper in the direction of subduction. So you can get earthquakes occurring all along the surface of that subducting plate. Other plate boundaries in the interior of some continents, for other plate boundaries, we're looking at divergent boundaries. So in those cases, we get normal faulting along divergent boundaries at the mid-ocean ridges especially. And along with that, we get strike-slip earthquakes along transform boundaries. Remember, when we have a divergent boundary like the mid-ocean ridge, it gets that stair-step or zipper look because it's divergent boundaries connected by transform boundaries, so they're right there together. And earthquakes along divergent boundaries, again, tend to be shallow and low in magnitude. So the larger earthquakes have to do with subduction zones generally, but you can also get large ones at transform boundaries like the San Andreas Fault. Okay, you don't have a place for this in your notes beyond what we just talked about, but if you've got room, you can put this in with describe how plate tectonics plays a role in the creation of earthquakes, or you can make some notes along the image, particularly if you want to write on the graphic for the divergent boundary in the upper right-hand corner of the page what's going on at each location. So the things that I have labeled on the image on my slide would be good for you to label as well. So looking at this divergent boundary, again pointing out that we have both divergence, okay, being pulled apart, and transform moving side by side. So we get an injection of magma where those plates are being pulled apart. So again, drawing on our knowledge from the plate tectonics section, when you have a divergent boundary and you pull those plates apart, you're decreasing the pressure at the center of that rift, which causes decompressional melting. Okay, so you're melting the rocks that are below it just by releasing the pressure on them. So in that case, you get an injection of magma, and the magma intrusion beneath the axis of the rift, right along the center, causes shallow earthquakes. Faulting near the rift, we get shallow, medium-sized earthquakes that occur along the axis of the ridge where normal faults down-drop blocks. Okay, that's what this, it looks like a bookshelf that's been knocked over, the rocks that are on either side of the axis of the rift there. That's what I'm talking about when I say the down-drop of the blocks. So those rocks have cooled and solidified, so when you push them apart, they're breaking along normal faults. And we also get faulting along transform boundaries. So shallow strike-slip earthquakes occur along those transform faults. At subduction zones, we're getting shallow earthquakes that occur in the trench. So right near the surface where our two plates meet at the trench and the accretionary prism, we're generating shallow but very usually strong earthquakes. So where the oceanic plate bends into the trench, we're producing earthquakes. Thrust faults in the accretionary prism produce earthquakes as well. The largest earthquakes are produced along the megathrust boundary. So that's where the overriding plate is thrusting up over the subducting plate. Movement of magma in the crust, which leads to volcanoes above the subduction zone, and the related volcanic eruptions produce earthquakes, and thrust faults that are behind the magmatic arc, or behind where these volcanoes are being generated, produce earthquakes. A good example of this is along the west coast of South America. So we've got the Andes Mountains here, where the oceanic plate is diving down below the west coast of South America. It's really cool, and that we can plot out exactly the depth and location of all of these hypocenters. So looking at the image on the bottom right-hand side of my screen, you can see the yellow representing the shallow earthquakes, the green representing the intermediate, and the red representing the deep earthquakes. So we can actually, just by looking at the data from these earthquakes, we can map out exactly what that subducting slab is doing. You know, you could just connect the dots and draw in what that subducting slab looks like. It's pretty neat, and this is relatively new that we're able to do this. It's really cool. Perhaps the most obvious plate boundary where you would be generating earthquakes is continental collision zones, because this is the one that I think of as a train wreck. You know, we've got these two huge continents that are equally matched, and they just plow into one another. So of course you're going to be generating earthquakes at that, especially at the initial impact. But continental collisions produce large earthquakes along the megathrust. Again, the megathrust where one plate is starting to ride up over the other one. And in the inner plate thrust fault. So that means the rest of the plate is slicing off into pieces, and that's what this series of thrust faults is. You also get continental strike-slip faults that can produce large but shallow earthquakes, and that's what these faults in the interior can be. All right, how could earthquakes be generated within continents? We've got several things going on. So earthquakes within continents, we can have continental rifts that cause shallow, moderate-sized earthquakes along normal faults. And we can have renewed motion on pre-existing faults that can produce large earthquakes. So for example, in Missouri in 1811 and 1812, there was some serious movement along a fault there. And it has not moved much since, but at that time it caused a lot of devastation, and now that area is very highly populated. So it's interesting to see that something that hadn't moved on a human scale in quite a while is still able to move. It can still be active because these things are occurring on the Earth's time, not on our time. Also, we can get earthquakes from magma rising up through the crust and faults in the interior. Different seismic waves. So this figure shows a block of crust, an earthquake location, and various waves that are generated underground and along the Earth's surface. The blue waves occur along the surface. The gray waves occur underground. The fault movement initially produces P and S waves. So the P wave is a primary wave, the S wave is a secondary wave. They travel away from the fault rupture, but when they reach the Earth's surface, some of their energy is converted into vertical and horizontal surface waves. So in your notes, we've got surface waves. What I want you to note here is that surface waves cause most of the damage. Surface waves cause most of the damage. Okay, the first type of surface wave we're looking at here is the Rayleigh wave, and that's a side-to-side movement. The motion is perpendicular to the direction of movement. So if the wave is moving, is headed north, then it is sort of snaking side to side, east and west, as the overall motion is north. Okay, it's a side to side movement. The second type of surface wave is the Love wave. This is a rolling motion similar to an ocean wave. The wave rolls in the same direction as it moves. Next we have the body waves. So again, the P wave is the primary wave. This is a compressional wave. it compresses in the same direction as the wave propagates. It can travel through solid and liquid and is the fastest seismic wave. The primary wave is the fastest seismic wave. That's why it's primary. It arrives first. The S wave, or the secondary wave, is a shear wave. They rock up and down, perpendicular to the direction of the wave propagation. So as the secondary wave is moving through the rocks, they're moving up and down perpendicular to the direction the wave propagates. And these can travel through solids, but not through liquids, and this is important. S waves cannot move through liquids. This is important in trying to image what is below ground, because if S waves are bouncing off when P waves are not, we know that we're dealing with a liquid.